Hello everyone. In today's video, what we are going to do is learn about single qubit gates and how they are used to manipulate single qubits. Now, even before talking about quantum gates, let's look at the classical picture for a few seconds, right? In our daily lives, we always use classical computers to do all sorts of crazy things, right? Like posting things on social media, doing complex mathematical functions. But how are these complex functions actually implemented inside the computer? They are actually done through classical gates. So we just have these ones and zero bits that the computer really can understand. And then we manipulate these ones and zero bits through these gates, which leads us to more and more complex operations. So if you put enough of these bits and classical gates together, you're going to get something like posting or video of your cat on Instagram, right? So let's just look at the classical gate, which is used to implement a half adder, the classical circuit. So what we have here is an AND gate and an XOR gate. So this is just a basic circuit to add two bits and give the result, right? So we have A and B. So let's just consider the value of A is 1 and the value of B is 1, right? So 1 and 1 would give us 1, which is the carry when you expect when you add the bits 1 and 1. And what is the sum? So 1 plus 1 will give us 0 in Boolean algebra. So the final result will be just 1, 0. And what if it's 0, 1, 1? So 0 and 1 and is 0, carry is 0, sum is actually 1. So what we would get there is 0, 1 or just the answer 1. So that is how the classical picture works. Now, how does the quantum picture really work? So the only difference between the classical gates and the quantum gates is that in classical gates we use something called Boolean algebra. In the quantum gates, they are much more advanced and they don't just work on these discrete 1 and 0 bits, they work on qubits, which are far more complex and can be in all sorts of states due to entanglement, superposition, and all sorts of things like that. So, in quantum gates, we use linear algebra, right, to represent our sort of quantum operations. Now, the thing about quantum gates is that the operations that they do are reversible. So, what happens? Classical gates are not, by the way. In quantum gates, what happens is you apply a quantum gate to a certain set of qubits. You can just apply the inverse of it to go from the result to the initial set of qubits. So, let's just get started implementing the quantum gates for now, and we are going to do it today on single qubits, right? So the first thing, let me just show you, I have this file down here, the single qubits.kh.qs file, the QSharp file. You can just write this sort of framework to get started. So what I'm going to do is use q is equal to qubit. So I'll just initialize a qubit. And now even before we go further, I just want to dump machine here and reset q. Right, so I'm just resetting the qubit before I release it, which we have to. Now, what the dump machine function is a very versatile function. It allows us to have a peek at the state of the qubits inside the simulator at a particular moment. So when I do this dump machine, you see the result down here. So you see the ket 0 state with 100% probability, and this is what we would expect, right? So when we initialize a qubit in QSharp, it gets initialized to the 0 state. Now let's start applying, get to the really fun part, and let's start applying our single qubit gates. So the first gate that we're going to apply is over here above my head, which is the Pauli X gate or the NOT gate, which is analogous to the classical NOT gate. So let me just apply, even before talking about it, let me just apply the Pauli X gate to our qubit. Now, what should we expect down here? Let me run it and let's see. Right now, you can see instead of the zero gate with 100% probability, I mean, zero state with 100% probability, we have the one state with 100% probability. So, all this X gate does is flip the qubit that we passed into the gate. So how does this work? You can see the matrix representation of the X gate over here, which is just 0, 1, 1, 0. Now let me just open my paint. Right, so this is how this is our X gate, which is represented in terms of matrix like this, right? And we have our initial state, you remember, was just ket 0 state, right? So when we apply this X gate to our ket 0 state, what happens? We just do this matrix multiplication. So 0 into 1 is 0, plus 1 into 0 is also 0. So we have the 0 right here. And 1 into 1 is 1, plus 0 into 0 is 0. So 1 plus 0 is just 1. So the final state that we're going to get is the get 1 state. And that is exactly what we have down here. Amazing, right? So that is the Pauli X gate. Now we are going to look at a very, very powerful gate, which is the Hadamard gate. So the Hadamard gate is what puts our qubit into superposition. So I'll just show you what that does. So I'll just change this X to H, right? So X for Pauli X gate and H for the Hadamard gate. So let me run it again. And now you can see. So we have this both the 0 and the 1 states represented in our qubit probabilities. Now here's the fun part, right? So we have 50% 0 probability and 50% 1 probability. So this is what the Hadamard gate basically does. It puts our single qubit into superposition so that it has equal probabilities of either coming out as a 0 state or a 1 state. Right, so amazing. That's another wonderful function. Okay, now let's quickly look at two other gates. The first gate that we're going to look at is the Pauli Z gate. This was the result of my Hadamard transform on my qubit, which had gave me a qubit with the zero state probability amplitude being 0.7071 and the one state amplitude also being 0.7071. Now, when I apply my Z gate to that qubit, right, and I run it, I'm going to get the same amplitude, but if you see my amplitude associated with the one state, I'm going to get it as minus 0.7071. Or in other words, a phase flip of pi radians has been applied to it. To put it in the simplest terms, if you started off with a state such as alpha 0 plus beta 1, my output state is just going to be alpha 0 minus beta 1. Finally, let's look at the rotation gates, right? So before that, we need to have a slight look at the Bloch sphere representation. So this is a Bloch sphere representation of a single qubit. Now, when we apply these rotation gates, rotation Z, rotation Y, and rotation X, we are rotating a particular qubit over either of these axes, right? So initially, our qubit is at a 0 state here when we've initialized it. Now, let me show you what happens when I rotate that qubit for, let's say, pi radians 3.1416 over the X axis, right? So in the Bloch sphere representation, we started off with a 0, and if I rotate this 0 qubit over the X axis, so this is the X axis, if I rotate it over the X axis, I'm going to come 180 degrees all this way here, and I should get the 100% probability of getting my one state. So let's just run it to check it. And without a doubt, that's our output. So we have a 100% probability of obtaining the one state. So these were the single qubit gates. I know there are more gates that were not implemented in this video. You can try them yourself. Now you know how to manipulate qubits. So keep enjoying doing quantum programming and keep watching this playlist. Thank you.